I'm going to continue the classes on generative AI architectures. There are, I think, more than 10 different generative AI architectures, and most popular one in these days are transformer model, that is basics of GPT, and second popular models are diffusion model, that is usually used to generate images. Sometime in the future, I believe that transformer model and diffusion model may be combined together to simultaneously generate images, sounds, and text together. Then you can make a movie using the generative AI. I think it will be realized less than 10 years. You may be in the age of 25, and 10 years later, still you are young, 35, so you have bright future to pursue that area. So, but problem of foundation model that is actually combining many different type of generative AI model has a big size. Number of parameters could be 100 billions or trillions. So it means that in order to provide the service of generative AI in a real time means if you input a text, in a millisecond you have to receive the generative text or images or movie sounds or something like that. Let's assume that everyone in this group, all the population people are using the generative AI at the same time. So that means it may be needed to have huge amount of computation. Probably 1,000 or million times more computational power are needed compared to current status. So that means our GPU and HBM semiconductor has to be 1,000 times faster than now, and 1,000 times more faster than now, 1,000 times more in parallel. I think in a word that can be said that we need an AI supercomputer. Believe in me, for the last 10 or 20 years, major technology innovation will occur in that area, not the mobile area. Many of researchers are still stay on the innovation technologies for mobile systems such as smartphone and edge system or automotive vehicles, but because we need huge amount of parameters and computing powers, we cannot put that into the smartphone or automotive. So I think technology will move or shift to the AI supercomputers. Now let's come back to the class. So there are many different types of generative AI architecture. One of the very fundamental architecture is encoder-decoder architecture. There are some variations depending on each applications. Probably next week I'm going to start with the generative AI model for sequential data, and one of the simplest model of that is RNN, recurrent neural network. But overall, looking at the overall generative AI architectures, most of them has encoder and decoder architecture. Encoder and decoder architecture means if we put the text or images into that generative AI, in the middle of that architecture, they transmit our human thinking or languages to latent space vector. And then decoder interprets that G vector, latent space vector, into the real world. So it usually has two different types of. I think this kind of architecture may came from idea of information theory. So one day I look at the textbook of information theories, and there are so many mathematics to explain this architecture, but nobody is actually interpreting that to me using human languages. They just use the mathematics. That's I don't like much about the information theory. But I have my own interpretations like church Bibles and something like that. So I will repeatedly gonna use that concept to explain this generative AI architecture. during the training process to optimize. So actually this encoder decoder is made of deep neural network. So that's why perceptron and backpropagation is basic building block of generative AI. But when you are training this encoder decoder, you have to evaluate current capability of an encoder and decoder. And if they are not good enough, you have to update the model parameters, the parameters of the deep neural network for encoder and decoder. And when we are evaluating the performance of encoder and decoder, we are using entropy concept. And how good the output it is, we are using the entropy. Summation of entropy should be minimized. Sometimes we are comparing the output with some reference data. In that cases, we are using the KL divergence. KL divergence is kind of comparing my own entropy with the reference entropy. So those two, entropy and KL divergence, are mainly used when we are, as a loss function, when we are training this encoder-decoder architecture. For example, one of the symbolic architecture is called as variable autoencoder or transformer model. Variational autoencoder architecture are later on evolved to gain and diffusion model. So VAE is a model architecture for very hot current generative AI model. As I know that you may have some experiences to use DALL-E, which the DALL-E is the OpenAI generative AI model. You can easily, if you put into a text, it will transfer to the image files. And DALL-E is a kind of diffusion model, and the model architecture of gain and diffusion model is a VAE. That's why we're gonna spend a couple of weeks to talk about variable autoencoder. And transformer model is actually mostly being used for large language model. And GPT. And sometime in the future, these models may be combined together to become a foundation model. Foundation model could be categorized as a multi-modal generative model. But surprisingly, most of this, so VAE gain diffusion model are mostly used for generating images and sounds. Transformer model is mostly used for text generation, more likely sequential data generation, and someday these two will be combined together. I'm 100% sure that at this moment, Google, Microsoft, OpenAI, and Meta are spending a lot of resources to develop multimodal generative model. If I'm right, next year you're gonna have a new news released on the press. If I'm true, please give me a copy. Okay. Originally, there were models named as a CNN, convolutional neural network. Usually, this type of a network is mostly used for classification. Classification means if you show a picture to your CNN AI model, it will tell you that this is a good guy or bad guy, or this is a cat or a man or a woman. It is mostly used for CNN, for classification. And this type of model came from RNN. RNN is mostly used for classification purpose. Some way it can use for generative purpose, but mostly for classification of sequential data. If you give my speeches to RNN model, this is about the generative AI classes, or sometimes it can classify what I'm talking about and what is the subject or what is the conclusion. Those kind of model is classified as a classification model. But right now, I think now we are living in an era of generative AI. Ten years later, please remember that we're going to have new models like a self model. This is my own classification saying that you may have certain AI model in the computer that has the same emotion as you, same ethics as you, and same identity as you. If you are Christian, this model will control the output of your generative model. And then this could become that is my whole picture of the artificial intelligence. Right now, to develop a human-like model in the future, maybe within 10 years or 30 years, now we are in a status of generative AI. And right now, we may have different AI models to generate different texts, images, and sounds, but someday they will be combined together to become a fundamental foundation generative AI models. And in addition to that, if you have a model that look like you, like same ethics and same morality and same understanding and same IQ, EQ, and like that, they will combine together. When they are combining together, actually, when they are combining two different models together, usually we may need reinforcement learning. Reinforcement learning is a kind of teacher or mother. Sometimes you stop the AI, sometimes you release AI. They are kind of gatekeeping so that your foundation model behaves like yourself. So in our class in this semester, we're going to start from traditional classification model. From next week, I'm going to start with the RNN. Then we're going to talk about variational autoencoder and GAN and diffusion model and transform model. At the end of class, I'm going to give you lectures on reinforcement learning. I think these are the overall picture of generative AI models in the market right now, and this also shows my future vision of evolution of artificial intelligence. I'm not expecting you to be an expert on all these models, but you have to be able to use this kind of model to increase the efficiency of your work. To have confidence when you are using this kind of model for your work, you need to certain amount of confidence. In order to do that, you need to understand basic architecture and principles. That's the main goal of this class. Now let's go to the encoder-decoder architecture. This is very building a fundamental building block of encoder-decoder architectures. Depending on different models, like again, diffusion model, LLM, or GPT, we may have slightly different shapes. But so far, I believe this is really the basic building block, and it's useful to understand the basic concepts of generative AI. We may have input vector that represent text, image, or sounds. In the future, it may have a mixture of text, image, and sounds. But right now, in the case of variational autoencoder, we are putting the images. And in the transformer model, we are putting the text. Then, your input vector is converted to G vector. That is called as latent vector. I think G vector represents the sounds of God. Human cannot understand. If you want to understand the meaning of G, you need to interpreter. That is called as a decoder. Computer is interpreting God sentence to human sentence. That is decoder. Training of generative AI means training of this translator. In the church, probably pastor or some people has to interpret Bible, and they have to tell us in a human languages. We don't understand what the God is thinking about. G is God. But interesting is that somehow G is a Gaussian function distribution. Probably in human world, we are very distinctive. Distal is very distinctive. Either 1 is 0. But in the God world, in the heaven, there is not clear difference between good and bad. This one has probability of good 99%. This has probability of bad 1%. And if we have 100 people in this room, some people are good, some people are bad, and distribution is Gaussian. And so that is the very good concept embedded into the generative AI. And one day, probably in October or November, I'm going to spend some classes to talk about why it should be Gaussian, why it should be certain have distribution. Interesting is, encoder-decoder is calculated using the GPU and memory. Those are distal computers. They are not Gaussian. Some people are trying to develop encoder-decoder using neuromorphic chip. They are trying to use analog circuit to do the mathematical calculation and storages. That may be very similar to what the God is doing, but very slow. God is very slow. Human is not patient enough. We need to have responses from generative AI in a second. Probably in automotive vehicle, in a 1 second means we are whether being killed or alive, millisecond or microsecond. In this architecture, God and humans are mixed together. Anyway, we have encoder. Encoder is actually deep neural network. Deep neural network. And the model parameter of the encoder is represented by pi. This is actually model parameter. And the generator has model parameter theta. We have to, during the training process, we have to optimize encoder pi and decoder theta. Encoder actually transmit human language X into the G space, heaven space. And so in order to training them, we need to update this pi and theta repeatedly. So we need huge amount of data. During the training process, we are using this kind of mathematical description. That means we have to train pi and theta to minimize the loss function. Loss function has two different elements. One of them is first requirement of training. Please remember that even though we are later on in this class we are going to talk about diffusion model and GAN and large language model and GPT, very similar. Mathematical description and architecture are very similar. So I'm spending more time to talk about this. First one is if we have an output, that amount of information should be minimized. Entropy should be minimized. Second requirement is KL divergence. My explanation about this mathematics is not rigorous. In order to induce all this equation rigorously, probably I'm going to spend a couple of weeks in October. But today, I want to give you the overall picture. What this KL divergence means is the entropy difference between encoder output, that is actually Q pi, and PG means the Gaussian distribution. So you have an encoder that translates your language to God language. That is Q pi. PG is regularized Gaussian function. Somehow it seems like in the God heaven world, every signal has Gaussian distribution. So they compare whether your encoder output is very close to God's language. How are you going to compare them? Compare entropy of your encoder output and entropy of Gaussian function. In this class, I'm trying to give you the overall picture of generative AI and what is the loss function. As I remember, I might be wrong, this error is called as reconstruction error. This KLD is called as regulation error. In reconstruction error, it is more likely interpreting the performance of decoder. Decoder is translating the G vector space to human space. And in the human space, what is good or bad is measured by using the entropy. How much information we need to describe the output. If we need 1 gigabyte memory to represent this output, training process seems like they don't like that. If we need just 1 K bit byte to represent the output, that is a good performance of decoder. One day I was thinking of why it is good or bad. Humans are very sensitive to resources and money, and in these days memory and GPU bandwidth. So somehow, if we need small amount of information to describe the output, that means a smaller number of entropy. That is what we like. That measurement is called as reconstruction error, and during the forward process and backward process, we are using this reconstruction form. Second term is called regularization error. That is looking at the in G space, G vector space. If encoder has a good performance, their output has to be very close to Gaussian distribution. Gaussian is a God distribution. So this means we have to optimize the encoder DNN architecture pi, and generative architecture parameter theta should be optimized to minimize these numbers. Now, somehow interesting, it is very hard to explain that. We have to go through this latent space vector. And what we found is that some of information, human information, is lost during this conversion process. I don't know. Whenever we convert human language X vector to G vector, somehow we are using computers. And also, even though we have optimized model parameter pi or theta, there might be some errors. More important thing is that all these parameters and data should be stored in memory. Memory capacity is not infinite. Sometimes we have to compress them. Sometimes DRAM is short-term memory. If you turn off the memory, it'll lose data. Sometimes it has an error, digital error, because of radiation of X-ray, or to reconstruct those errors. In these days, DRAM and GPU are using error correction code. Joungho, do you remember parity check bit in digital? So we need extra bit to reconstruct the errors. So that means another resources are needed. So naturally, our computer is not infinite. Also, sometimes if the input is sound, we have to have AD converters, analog to digital converters. There are certain amount of errors are always there. So because of that, this encoder decoder has certain errors and memory effect. The good thing about human is that we forget what was happening yesterday. For example, I have an argument with my student Joungho yesterday. Today I give a coffee and smile, we are good again. Because we lost bad emotions after sleep or something like that. But digital memory is not good person. They have longer memory. But eventually they are losing their memory. So in order to connect between encoder and decoder, some of the data at the encoder is directly supplied to decoder. That is called as attention network. That means we have more network to train. Attention network is also represented by deep neural network. In GPT, like transformer model, they may have many number of attention network. So that means we need extra memory and extra network to be trained. So the generative AI architecture is becoming more complicated and more complicated. When I am giving you lectures on transformer model, main focus will be how to design this attention network. If you have a book, sometimes you have to remember first sentences at the end of the book reading, because some of the meaning of last sentence is actually related to the first sentence. Today, I'm having a class at KAIST, and last class is I'm happy. That means the class is happy. So we have to have a certain connections. So, but in the world, we have billions and billions of books. We have to make all the connections. Without attention network, we found that some of the context in the X vector is not recovered. Overall, they are recovered, but some of them are not recovered. So we intentionally added another deep neural network that is called as attention network. That is very core part of GPT. Now, let's assume that we finished the training process of encoder and decoder. Then what are you going to do when we are generating a new text? Then this decoder is used for generative purpose, generation. For example, we have G vector space that represent tiger. And if you have another G vector that has distribution of cat or dog, then if you combine them together and put into this decoder, the output will be a new image that has 50% tiger, 50% dog. So one of the methods to generate new images or text is to work on the G space. So after training, this part can be used as a generator. Another way of generation is you are having another network that translates G1 to G2, and you put into them. Let's assume that you have encoder that is transmitting text to G1. And G1 is a kind of latent vector space representing the text latent space. You can also design a new network that is actually transformer. You can also design a transformer deep neural network that transform G space to G space. One of the G space is representing the text G space. Another one is the sound G space. Then if you input text G space is converted to sound G space, and sound G space will generate the sound. So there are many different variations of generative architecture. But I'm sure this is the main concept of most of generative AI model. And from next week, I'm gonna give a lecture on RNN, transformer, GAN, diffusion, and this type of sequence. And at the end of the class, I'm gonna spend more time on reinforcement learning, how to control this generative AI, how to make this generative AI model to be a good boy. Sometimes if you does not control them, it's gonna be a bad boy. When we are applying reinforcement learning for AlphaGo game, good boy means winning boy, bad boy is the losing boy. So we can give them our target, and that is expressed by a reward. In reinforcement learning, we have a reward, and reward is represented by a mathematical formula. In your term project, you may have to define what's good or bad. That is symbolized as a form of reward. And by applying the reinforcement learning, you can train them to be a good guy. But generative, compared to classification AI model, generative AI model need much more complicated training processes. And also you have to combine them together. Also you have to make them a good boy. Reinforcement, huge amount of computational power are necessary. That is so that means you need more money. And so some rich guy or rich companies can have this kind of capability. Poor people does not have that access. So poor people become more poor, and rich people become more rich. I don't know if that is what we want, but that is the nature of generative AI model. This is more likely VAE architecture. Another generative AI architecture is diffusion model. In the class of microwave theory at high frequencies, if we want to measure the impedance of an object, we have to send a wave, and we measure the reflection. That is called S parameters. When in high frequencies, actually we cannot touch. If we want to touch, there are certain distance, my finger length. If we have a certain distance, there will be phase delay. So we cannot actually measure real identity of this object. So in microwave theory, we are sending wave, and we are receiving the reflections. If impedance is matched 50 ohm, there will be no reflections. So if we want to measure whether the termination is 50 ohm or not, we cannot measure using the tester, because tester has certain length of cables and probes. So we cannot measure the identity. So rather than using those testers, we are sending waves. If there's no reflections, we feel, oh, this is good matching. Same principles are used. In variational autoencoder, we have encoder and decoder are separated. But here is that this process is encoder, this process is decoder. So during the encoding process, we are converting our input to the G space. And we have to reconstruct, and we have to reconstruct the only original images. Similar to this variational autoencoder, after the training process, we are only using the decoder architecture to generate the new images. In this year, most popular, most exciting generative AI architecture is diffusion model. I think they got idea from VAE, and rather than have two different encoder and decoder, they are using the same deep neural network for encoder and decoder. We're going to spend 2 weeks to derive all the mathematical description of entropy and the KL divergences. Here, same. During the encoder process, they are intentionally adding a Gaussian noise. So initial image is like a human picture, and in the G space, it is a kind of noise. Mathematician or electrical engineer say it is a noise. I think it is a speech of God. Basically very similar, but so this process is called noising process. This decoder is called a denoising process. How good is the noise? We have to, during the training process, we have to evaluate how good this encoder process is, noising. And intentionally, we add Gaussian noises. At this final stage, this is really noise. But how good it is, we are using the KL divergence mathematics. So this KL divergence is mathematics is a kind of mathematical formula whether this is a good God's language or not. Why is that Gaussian? Maybe God is noise. And now this noise is reconstructed back to the original file images, and we have to compare them. Entropy is being used to compare whether this is the same picture as not. If we can reconstruct same image as good as similar as the original one, we feel like, oh, this is good encoder and decoder. Later on, we are using the decoding process. Don't worry, we're going to spend many hours to talk about this mathematics and how to implement. There are some convergence between x0, x1. Originally, your image has certain distribution. But if you add more or more Gaussian, and noise is the distribution of x becomes more like Gaussian, and noise is almost very broad. So we're going to observe these Gaussian distributions, and deep neural network will work to convert from previous state to next state. So DNN is actually adding noise. And during the denoising process, DNN network is capable of to remove the noise and deconstruct images. in the graphical represent this, your original image has certain point. Your eye and ear has a certain position. But here is likely certain distributions. This eye, one point A has certain Gaussian distribution. Later on, if you want to design a new images, you may have different distribution of this one. You have long ear, short ear. You may combine them together to reconstruct new images. Then you may have right ear has the sharp ear, and left ear may have long ear, something like that. I was spending a couple of years to understand many different generative AI architectures, and this is my personal interpretation of architecture. I believe there are not more than that architecture. I checked the MIT architecture, Stanford, not much more than that. They just write down the mathematics. Another popular generative model is called as GAN. Adversary network, It has two different components. Generator has certain architecture, and it transmits G space vector to X space vector. Encoder, we have generator who has latent space vector G, and it transmitted to human data. And we have generator. But in this generative advisory network, we do not have encoder. But we have a discriminator. Discriminator network has, rather than have encoder, they have a discriminator network. So if you have your input, output, and reference data, you compare them. So for example, we are asking generator to draw an image of Picasso, and X is the output of generator output. And this X dash is a reference. Discriminator output is whether it is good or bad. Only two output, 1 or 0. In variational autoencoder, encoder and decoder are working together very cooperatively. They help each other during the training process to minimize this entropy and KL divergence. They are working together to make a good generations. And when they are working together, they have to communicate each other. They are communicating through the God space or sometimes directly. But in generative, again, generator and discriminator is not working together. They are fighting each other. Rather than using entropy and KL divergence loss function, we are training this D, discriminator network. So rather than using the information theory and mathematics represented by a KL divergence and entropy, we are training the loss function. Loss function is actually a discriminator deep neural network. We are trained this generator network and discriminator network to fight each other. So that at certain point, they said, no more game, I'm done. And at some point, discriminator say that you are good, I'm done. At that point, they stop the training. So sometimes you have to choose certain generative AI models. I would say there are 3 criteria. One of them is high quality. Second criteria is fast. So speed. Third one is mode. I think we have 3 elements when we are choosing one of the generative AI. If we use, sometimes you use variational autoencoder, or sometimes transformer model, and sometimes I think we may add cost in addition to that, then you can choose that. Some model may ask 1,000 GPU boards, sometimes you may need a couple of boards. But anyway, sometimes you are using variational autoencoder or GAN or diffusion model or transformer model to generate images. And you can easily see the image quality, how much resolution, whether it is clear or foggy or something like that. Second is, some of the model takes an hour or a day to generate new images. Some of them give you an image in a second. So that kind of performance. Third one is mode conversion diversity. That means I can ask the generative AI model to make images of a dog. We may have 100 different cases of different dog, Caucasian, or what is your dog's name? Hyuna, do you have a dog in your home? No. What about Jungmin? Who are raising kids? What is pepper? What is the species? I mean, poodle. Okay. So there are 100 different of dogs, but some image only make output of poodle only. So diversity is also important because when we are generating new images, we are not expecting to generate same images all the time. So diversity, as I know that GAN is good for this area, and diffusion model is good for this area, and variational autoencoder is good. So it seems like you have diverse output images. You have to choose whether VAE or diffusion. Probably diffusion may take more computational power, that is slow, and GAN but VAE does not have very good quality output. Sometimes you have to use VAE or diffusion model. But what I know is that diffusion model is very hot subject in these days, stable diffusion. Thank you for your attention. This is the summary, not the final, summary of overview of generative AI. Thank you for your attention.